Welcome back to Arts Learning. In this video, we'll be going over the hardest problems from the PDF I sent out on momentum. Okay? Where can you access this PDF? I'll link in the description below, but I'll just tell you now. It's on artslearning.com in the physics section and inside Unit 5 folder. Okay? So let's start then. Let's go over what these hardest questions are, and they might not be the hardest, but also conceptually deep. Okay? That's why I picked a variety of questions. And if you want answers to the questions that I didn't answer in this video, as always, you can just check the answer key on my website on this PDF. Alright, so let's get started. The force versus time graph below acts on a 2 kg object. Its mass is equal to 2 kgs. That starts moving at positive 10 meters per second. Velocity is 10 meters per second. We need to find the net impulse over the full interval, okay, the object's final velocity, and the exact time at which the object is momentarily at rest. Okay, so to find the net impulse over the full interval, that's what? That's net J, right? And the area under a force versus time graph gives you impulse. So in order to find this net area, you remember what we did when we had displacement in Unit 2? We subtracted the negative area, we subtracted the area below that axis from the area above that axis, right? We considered this as positive and this as negative. So how are we going to find the area of this? This is going to be 6 newtons, right? The height here, and then 2 seconds here. So the area of the positive area here would be 6 newtons times 2 seconds minus, what's this going to be? The area of the negative side, right? I already put the minus here, so I don't need to put a minus inside the other brackets as well. So minus, so from 2 seconds to 6 seconds, right? So that's 4 seconds here. That's how wide it is. 4 seconds times what's the height here? It's 10, right? So 10. And 10 newtons. I'm not going to put negative because I already put the negative out here. So 12 newton seconds minus 40 newton seconds, which is going to give you negative 28 newton seconds. All right? That's your net impulse. So that means it gained a bit over here, I can see here, but then it also lost a bit. Actually a lot, not just a bit. Okay. So now let's look at the object's final velocity, right? So at the end of this, change in motion here, what's the object's final velocity? Well, how do you find that? First, you have to look at the change in momentum, right? If you have the mass of an object, if you find the momentum, you can find the velocity, right? So we need to find the final momentum here, because that's going to be equal to the mass times the final velocity, right? So the final momentum, what momentum did we start with? We started with P initial, right? P initial plus delta P. So P initial here would be 2 kgs times 10 meters per second. That's our initial velocity, momentum, right? So 20 newton seconds. And delta P was negative 28, right? So we can just write P final here as 20 newton seconds minus 28 newton seconds, or negative 8 newton seconds. All right? So that's our final momentum. So we know that P final is equal to M times V final, right? Whoops. Okay. So then we know that negative 8 newton seconds is equal to mass, which is 2 kgs, times velocity final. And velocity final is equal to negative 8 divided by 2, or negative 4 meters per second. Okay, and that's how we find the velocity final. Now let's look at what it's asking us at the end. The exact time at which the object is momentarily at rest, which, if you know what that means, that's velocity equals 0, right? So we can understand that from here our velocity is changing very rapidly, right? We're having a lot of hectic changes here. So we need to find a way to pinpoint where our velocity is what it is. And how are we going to do that? Well, in order for if velocity is 0, right? At the point where the object is momentarily at rest, where velocity is 0, since momentum is mass times velocity, momentum would also be 0. Okay? So then that means that using this, right? Using this, we can figure out that 0 momentum is where we have a velocity of 0. Where do we hit a momentum of 0? Well, we don't know that, right? But we know that we have a lot of change here. So we can represent P final as P initial, which is, or we can start here, right? We can start here. We can say, at that point, my momentum is, well, let's see, it's forced Newton's times seconds, or, so at that point, my momentum would be at 2 seconds, right? T equals 2 seconds. P is equal to 20 plus 12. And why is that? That's because initially we had 20. Let me get a lot of this stuff out of the way. The area under this was 12, right? Initially we had 20 momentum. So after the first 2 seconds, we know that we're going to have 32, right? So 32 minus, because what's the area of this big block here? That's 4 times, here is negative 10, right? So this is negative 40 here. But that distribution doesn't happen immediately, right? It happens over a progression of seconds. So each second, how much do we lose? In total, we lose 40, and it's even loss, right? And how many seconds do we go over? 4 seconds. So 40 divided by 4, because that's the rate of change per second, right? And that's going to be times t is equal to 0. So you can find when exactly you hit that. 32 minus 10t is equal to 0. T is equal to 32 over 10, or t is equal to 3.2 seconds. All right? But remember, that 3.2 seconds is from here, right? Because you started here and then you're like, oh, I progress, and then this is around where I get my velocity of 0. But you have to remember, your actual start of motion was around here, right? At 0 seconds. So you have to add this 2 seconds that, that you skipped, you deemed it as 12. Or another way you could have done it is you could have gone 32 minus 10 times t minus 2 to denote that you went 2 seconds above. And then you would have gotten 5.2 as your answer, which is what the answer is, right? The answer wouldn't be 3.2 because that's after this point, right? But you have to count, in fact, that we started 0 seconds. So how many seconds did we skip? It's 2 seconds. After that, we started counting. So it's 2 plus 3.2, or 5.2 seconds. So solving this would also get you to the same place, okay? So you could just also solve this equation, 32 minus 10 times t minus 2, which denotes that you skip 2 forward, right? Okay. So now let's go over another problem that I wanted to go over was problem 9. Yeah. A 12-gram bullet. So before I even write anything, you remember momentum is measured in mass times velocity, and that mass is in kgs, right? Momentum's quantity is kg meter per second. not gram meter per second. So we need to convert this to kgs. 0.012 kilograms. It's fired horizontally into a 2 kg wooden block, hanging at rest from a string. Or in other words, a ballistic pendulum. Okay? The bullet embeds and the block plus bullet swing up to a maximum height of 0.18 meters above the starting position. So it looks like this. Okay? We have a block, the bullet comes into here. This is the before picture, okay? Afterwards, the momentum causes the block to go upward with the bullet embedded inside it, okay? So it moves a height of 1.8 meters. So what collision would we call this? A perfectly inelastic collision, right? Because the bullet embeds itself inside the block. And we need to find the bullet's initial speed. So let me start by writing out an equation here. M, so actually let me denote this as 0.012 times velocity initial of the bullet, right? We don't know what that is. So that's the velocity initial of the bullet. That's the entire momentum our system has, right? The hanging mass has no momentum. It has no velocity. So all of our momentum is coming from the bullet. So that's equal to, if you remember how we denoted inelastic collisions, we added the two masses up, right? Because now they move as one. So 2 plus 0.012 or 2.012 times velocity final. We don't know what the velocity final is. All right? So we have an equation now, but also remember that we can't solve this because we have two variables, right? We can use the height change, however, to give us an advantage. What do we know when the bullet embeds itself in the block? It grants that block kinetic energy, right? The kinetic energy moves it upward to a greater height. And so the kinetic energy changes to what? Gravitational energy, right? Because this block is going to hang like that for a sec, and then it's going to start its downward arc. But when it's just hanging there, that's your gravitational potential energy. Okay? Because it's not moving. So at that point, it's just only gravitational potential energy. But here, it's kinetic energy. Okay? So 1/2 mv initial squared, right? Because that's just the block, right? That's okay. So actually, let me denote this as mv final, right? Because it's a combined mass. So whatever this combined mass's energy is that pushes it forward, upward, that's going to be equal to mgh, right? Because it's going to stay there. That's the conservation of energy here from last unit. We can cancel out the m's here, and we're left with 1/2 v final squared is equal to 9.8 times, what's the height gain here? 0.18, right? So velocity final squared is equal to 9.8 times 0.18 times 2. And velocity final is equal to the square root of all of that. Okay? But what you have to remember here, you have to be careful, right? Because there is a trick here. And that's going to be the fact that you see how initially we have, this is velocity final, right? You want to remember this is not the velocity initial. So even if we solve for this, we don't get our velocity here. We need the bullet's initial speed, not just this initial speed. Okay? So v final is equal to, you don't need your calculator here for this, 9.8 times 0.18 times 2, and the square root of that, about 1.878 meter per second. Okay? So then from here, where can you go? You can just say that, you can substitute this back in, right? 0.012 V initial is equal to 2.012 times 1.878. And then you can just V initial is equal to 2.012 times 1.878 divided by 0.012. So let's try that out, see what we get. Then divided by 2 decimal digits in the denominator is going to give us a big boost. This is approximately equal to 314.87 meter per second. Or 88. I'll round it to 88. And the thing is, if you use because here I directly substituted, right? I didn't substitute directly. I used 1.878. So I did round it a bit. If you didn't round it, you might have got a different answer than me, okay? So I would actually advise to not round it, right? So I'd have probably pressed answer on my calculator instead of typing in 1.878. But either way is fine. So you end up with around 315 meter per second. Now we're going to go over problem 12. Okay. A 2 kg glider. So 2 kg glider. So don't know too much what this looks like here, but I'm just going to give it my best guess. It's moving right at 5 meter per second. Okay. And it collides with head-on and elastically with the 4 kg glider. Moving left at 3 meter per second. And we can say that this is perfectly elastic. Okay. Alright. So then how are we going to find both final velocities with the direction? If it's elastic, what does that mean? Kinetic energy and momentum are conserved, right? So we have 2 equations we can use to find it. When it's inelastic, only momentum is conserved. But now we have one more equation we need. So let's find the total momentum of the system first. 2 times 5, right? So 2 kgs times 5 meter per second plus 4 kgs times negative 3 meter per second, right? It's going in the opposite direction, is equal to, well, that's just 10 minus 12 or negative 2 Newton seconds. So that's our momentum initial, right? So our momentum final must be the same as that. So negative 2 Newton seconds is equal to what? Our momentum final, right? For the 2 kg, the 2 kg guy will the 2 kg glider will have its own velocity, right? It'll have its own velocity. We don't know what that velocity is yet, so I'll just label it as V1. Then the 5 kg, or the 4 kg will also have its own momentum and velocity. So 4 times velocity 2. You can divide the entire equation by 2, and you'll get V1 plus 2V2 is equal to negative 1. Okay? And that's how you solve this. You have one part of the equation, now you need this other one, which is kinetic energy. What's the total kinetic energy of this system? 1/2 times 2 times 5 squared, right? 1/2 mv squared plus 1/2 times 4 times 3 squared, which just give us 25 plus 18 or 43 joules, right? And then I can raise all this and I can say that 43 joules is equal to the final kinetic energy. The final energy, right? Which is just going to be kinetic. So I can just say final kinetic energy of 1/2 times 2. For the 2 kg, what's the velocity that we depicted? V1, right? V1 squared plus 1/2 times for the 4 kg, V2 squared. So we can just multiply by 2 here to get rid of all these 2's, these fractions. And we get 86 is equal to 2v1 squared plus 4v2 squared. Okay, then we can divide by 2. So I probably shouldn't have multiplied here if I'm just going to divide, but it's whatever. v1 squared plus 2v2 squared, right? And then we can just substitute in one of these equations. So let's just say first I want to find v1, or first I want to find v2. So we can just substitute this in for v1. Okay, so 43 is equal to negative 2v2 minus 1 squared plus 2v2 squared. 43 is equal to v1 is 4v2 squared plus 4v2 plus 1 plus 2v2 squared. 43 is equal to 6v2 squared plus 4v2 plus 1. And then 6v2 squared plus 4v2 minus 42 is equal to 0. Divide all of them by 2. 3v2 squared plus 2v2 minus 7. Whoops, not 7, that's way off. Minus 21 equals 0. Okay, so then we have, can we factor this anyway? Let's see. We have negative 36, right? And we have 2 here. So what adds up to negative 36 and makes 2? What multiplies, sorry, to negative 36 and makes 2? Well, there's 2 6's there. 18 and 2. 9 and 4. Or there's just nothing possible, right? That's also a scenario here. So then we could just plug and chug, right? We can just use the quadratic equation here. Negative 2 plus or minus square root 2 squared minus 4 times 3 times negative 21 all over 6. So let's find out what that looks like. So 3 h squared plus 2v2 minus 21. And we have 2 answers here, okay? I have 2 answers. That makes sense because I'll explain why in a second. Okay, so what you can look at here is that we have 2 answers of negative 3 and 2.33. But think about it. For velocity 1, if velocity 1 was negative 3, doesn't that just mean it's this? Right? We can't have that, can we? Because they don't elastically collide and then swap velocities. It doesn't work that way. This is assuming that velocity 1 was for mass 1, which we don't want. So we're just going to pick 2.33. Okay? If any of your final answers is over here, in this section, 5 and 3, it's wrong. So 2.33 is going to be our velocity 1. And then we can just plug that in to here. 2.33 is equal to negative 2v2. Right? So plus 1 over negative 2 is equal to v2. And that should give us about, so negative 2v2 minus 1. And so we actually found v2. Whoops, sorry. So that's I almost made a mistake there, right? That's why I was wondering. v2 is equal to negative 3 or 2.33. So v2 is just 2.33. Okay, because v2 being negative 3 is the same case here, right? We're starting where we ended, which we don't want. We want to look at something different. We can't have it being -3 again. That's just the start. We want it afterwards, right? So we're going to look at the other solution here. So that's 2.33. V1 is equal to -2.33 minus 1, or, so let's see, this is about -5.66. Okay, so that means 2 kg glider is going 5.66 meter per second to the left, and 5 kg glider here. So 5 kg glider, 4 kg glider is going 2.33 meter per second to the right. Because positive and negative denotes the direction here, right? So that makes sense. And now, so we can move on to our next question, but before that, I just wanted to give a quick, reminder over here that V1 and V2 are different, right? They're not the same. That's why you have to keep them separate and solve them using a system of equations. Otherwise, you can end up with something that's wrong, which we, again, don't want, right? Right. So now let's look at problem 15. Problem 15 is a 0.5 kg puck moving east at 4 meter per second, a hockey puck, and then that sticks to a 0.3 kg puck over here. And so this is the green one, moving at 6 meter per second in a direction 40 degrees north of east. Find the speed and direction of the combined pucks. So, in order to do this, you have to understand that previously I showed you pieces, where pieces was just one of them, right? But here, pieces is combined between these two. What do I mean by that? Well, I'm going to show you. Pieces is the x momentum of the 0.5 kg here, which is to the right? So I'll count it as positive. So 0.5 times 4 plus the x momentum of the 0.3 kg, which is 0.3, but times 6 times what? The x vector here, which is the cosine of 40. So this should give us about 0.3. The first one is pretty simple. It's just 2, right? 0.3 times 6 times cosine 40, and that plus 2. So px is about 3.3789, okay, Newton seconds. And py is going to be, so this one doesn't have a y component, right? So let me erase this stuff now. Let me just keep the angle. This one doesn't have a y component, the 0.5 kg, only this 0.3 kg, right? So 0.3 times 6 times sine of 40, which is the y component here. Since it's going up, I'll count it as positive. So what's that going to be? That's going to be times 6 times sine 40, about 1.157. Okay, Newton seconds here. Now, we're going to look for the combined speed and direction of these pucks. So like I said, right, px was equal to m times vx. Px here, so 3.3789. What's our total mass? That's going to be, since they stuck together, they're going to have it's an inelastic collision, right? So they're both going to have a combined total mass of 0.5 plus 0.3 times velocity x, which we're trying to find out, so we obviously don't know that yet. Velocity x is just going to be 3.3789 divided by 0.8. which is 4.2236 meter per second, velocity x. Okay? Velocity y is just py over m total. So 1.157 divided by 0.8, which should give us about, let's see, 1.157 divided by 0.8, 1.446 is equal to Vy meter per second here. Okay, so that's that. Define the combined speed. So magnitude of V is equal to the square root of Vx squared plus Vy squared, right? So V is equal to the square root of 4.2236 squared plus 1.446 squared. So let's see what that looks like. And you might get a different answer than me based on whether you round it to the same decimals, right? So I'm still plugging it in. And the total speed here is about 4.46 meter per second. Let me scroll up a bit so you can see. Yeah. And then what's going to be our direction? That's just theta is equal to arctangent of velocity y or velocity x, arctangent of 1.446 over 4.2236. So about, let's see, over 4.2236, 18.9 degrees. So 18.9 degrees. And that's going to be, so that's going to be, since both of these values here are positive, y and x are positive, we have a right arctangent value, right? But as I like to keep reminding people, if you have a negative and a negative x and a negative y, doing arctangent of those values, because the negatives over the negatives cancel out, you'll still get a positive angle here. So you have to add 180, because the arctangent domain is only from negative pi over 2 to pi over 2. I'll go over that a bit in my pre-calc video, so if that doesn't make sense much, make sure to check those out. And I would denote this as, so this is going to be north of east, right? Of east. Because, I mean, it's going northward from the eastward direction. So here, this is a very similar question, okay? So I don't want to go over as two similar questions, because that you can practice by yourself, right? I want to leave some questions so you can practice by yourself. I just want to go over the hardest in each section, so we have a good conceptual grasp as well as good rigor. Okay? Here, so a proton moving at 4 times 10 to the 5 strikes a second proton in an elastic collision. You remember, if two masses are the same and they collide, the degrees made here are 90 degrees. Since this is 30 degrees here, this would be 60, right? And then you can find the velocity magnitudes by using sine and cosine equations, right? They're very similar to the tension ropes. Velocity 1 cosine theta plus velocity 2 cosine theta here has to be equal to this x magnitude, because this is only x, right? And then the velocity signs have to cancel each other out, because this one has no y direction. But that I'll just leave it to you, okay? Because it's pretty simple. I just wanted to mention how to do it, because it could be tricky if you don't know the fact that in an elastic 2D collision, they separate at 90 degrees. All right, so yeah, let's try problem 18. This one is more of, everything you can have here. So a 0.02 kg bullet moves east at 400 meters per second, embeds itself in the 3.0 kg block resting on frictionless ice. The block plus bullet then slide east and collide with a 5 kg block, moving north at 2 meters per second. These two stick together. Find the velocity of the entire mass. Okay, so here, our initial Earth's momentum is 0.02 times 400, right? That's going to be equal to, so they collide and stick together, okay. And then here, this is going to be inelastic, right? So it's going to be 3.02 times the velocity of that. So in other words, let's find out what the velocity here is. I don't think it's really needed, but I just want to show you what it would look like, okay? 0.02 times 400 divided by 3.02, about 265. Velocity final is about 2.65 meter per second. This is in the x direction, okay, off the combined block here. And then they hit another block, a 5 kg block, moving north at 2 meters per second. So that's good, right? So that's that. And then what's going to happen here is they're going to combine and move like this, right? How are we going to find that? This velocity here. So we know that since we have a velocity x of 2.65, our momentum x, once we hit this, okay, once the collision happens, we're going to have a total mass of 5 plus the 3.02 mass, okay, times the, so wait, px, this is, so almost correct, but the thing is after that they're going to have an angle, right? So I don't want to use that right now because we don't have an angle yet. So px is just going to be this momentum here, right? Which is just going to be 0.02 times 400 or 8. We know that from right here. It's nothing new, right? We know the bullet's x momentum is just going to be the entire block's x momentum. The y momentum, though, we haven't solved for yet. 5 times 2, or 10 Newton seconds, right? And then what we do is we're going to use these to solve for momentum total, right? So, not momentum total, sorry, velocity total. Velocity here, so this velocity here is just going to be velocity, so wait, velocity, right, speed, in this case, y is equal to 10 divided by 8.02, right? So what am I saying here? This here is a total mass. So once the mass combines, it's going to have an x and a y velocity, right? But it's going to retain the same momentum, which means px, which is 8 Newton seconds, still has to be equal to 8.02, which is a new mass weight, right? Sorry, mass. So 5 plus 3.02 from here times velocity of x, right? So velocity x here is about 8 divided by 8.02, or 0.997 or 8. Let's just round it to 8. Yeah, meter per second. And velocity y is going to be py divided by m total, right? Very similar to the processes we took before. Velocity y, py here is 10 Newton seconds divided by mass total, which is 8.02. So velocity y should give us 10 divided by 8.02, or 1.247 meter per second. So velocity total, so the velocity magnitude here, squared, is equal to the square root of of 1.247 squared plus 0.998 squared. So let's, yeah. And then if you take the square of that, so let's see what that gives us. 0.998 squared, or 1.597 meter per second. So that's our total speed, okay? The direction of that is our arctangent of our velocity y, which is 1.247, over our velocity x, which is 0.998. So it's going to be about, let's see, 551.33 degrees. Okay, and since it's both, one is going north and one is going east, it's going to be northeast or north of east. Okay, and then the final problem, the final challenge here to tackle, problem 20. A 1200 kg car moves east at 16 meters per second and collides with a 900 kg car moving north at 20 meters per second. They stick together. Find the wreckage's speed and direction. Okay, so what that's going to look like is, we need to do this very similar to what we did before, right? Momentum x is 1200 times 16. Momentum y is just this, 900 times 20. So let's find these values first before diving deeper into this. 19,200 Newton seconds. And here, 18,000 Newton seconds. So that's the momentum, right? In order to find the final speed and direction, it's going to be Px is equal to, so Px is going to stay constant, right? Very similar to what we did before, even after the collision, because of conservation of momentum, is equal to these two added up, which is 2100, right? Because inelastic collision, right? They stick as one great mass times velocity x. Velocity x is equal to 1920, so 19,200 or 2100. Both of these go away. 192 divided by 21, about 143 meter per second. All right. And after this, we're going to look at the velocity y. Velocity y is going to be py divided by m total. Because similar to what happens, right? After the collision, the momentum is still going to be preserved. So we know that even with the total mass, we're going to have a new velocity, which preserves the same y momentum. So here, what's our momentum y? 18,000 over 2100. Okay? So 2100. Yeah, 2100, because that's our total mass. Remove both those zeros and get about 8.571. Do I want to include 1 or just leave it here? 57 meter per second. Okay? And then total speed is just the square root of 8.57 squared plus 9.143 squared. So let's find that. 8.57 squared plus 9.43 squared. 9.143, right? That could give me a slightly different answer if I did that. 12.532 meter per second. And our direction here is theta is equal to arctangent velocity y here, which is 8.57, divided by velocity x, which is, I didn't highlight it, so I'm having a bit of trouble. Yeah, 9.143. Or approximately, let's see, arctangent 8.57 divided by 9.143. So approximately 43.147 degrees. Since they're both also going north and east, I know you're getting tired of this probably, but still north of east. Okay. Although do remember the arctangent is a bit dangerous in that it gives you only one answer even if both of your things were pointing in a different direction. Okay. But that's only part A of the question. What's part B here? The percentage of the system's kinetic energy lost in the collision, right? So let me actually move this stuff so I have more space here. A kinetic energy initial, we have two parts of kinetic energy, right? Both this car and this car. So the kinetic energy of this car, 1/2 times 1200 times 16 squared, plus the kinetic energy of this car, 900 times 20 squared, which is equal to 600 times 16 squared plus 450 times 20 squared, or about 333,600. So 333,600 and joules. Okay, our kinetic energy final is 1/2 times what's our mass now? It's a combined mass, right? 2100 kgs. What's our final velocity? Well, we have that. That's why it came in handy, right? We need to calculate it again because we couldn't have just used regular velocities here. It looks like I erased it. So 12 point, if I remember, what was it? 12.532. 12.532 squared. Okay. So 0.5 times 1200, or sorry, 2100 times 12.532 squared, which is about let's see. Yeah, it's about 160, so 16,490. Or whoops, why'd the heart come? 164,000. That's why 16 wasn't working out, because there were 6 digits. 1,903.58. Okay. So what's our total energy loss here? What's the percentage of the system's kinetic energy lost? Well, that's just this over our total kinetic energy, right? And let's see what this gives us. So I got about 49% here, 0.494. So approximately 49%. Okay. And I know that the answer key shows us something a bit different, right? Because I use something different here. Instead of rounding, there's a few rounding errors, okay? There's a few rounding conciseness and a bit few errors as well. But that's fine, right? As long as you show your work, teachers should know that you did it right. It's just that you had a few errors in the rounding process, okay? It's completely fine if you got tinily different answers, but if you get like a whole different answer, then that's something wrong. If you got something close, that's just probably rounding, okay? And there's no real way to round. As long as you write everything down, you probably get the credits. That's why showing your work is pretty important. Okay, and that's it for this unit, okay? Next unit will be starting on centripetal acceleration, Coulomb's law, electric fields. And stay tuned for that one. Okay? Right, and make sure to give me a like and subscribe so I can continue helping you as well as others on their journey to experience physics the way it's truly meant to be experienced. Not through just boring memorization, right?